Hello guys, so it's been a quite long day since I have uploaded my tutorial. I was quite busy with my schedule in DNAG because of a deadline. So I'm here back. So let's see what we are going to create today. So as you can see on my screen, I have created this cool Vellum abstract. I saw this on a Reddit post and I try to recreate that. In this tutorial, we will see how we can scatter the petals, and once we scatter the petals it will have lots of interpenetrations. So we will go on a method that how we can remove all the penetrations, and then we will make this kind of wavy animation based on a marks attribute, and then we will render it. So let's dive into Houdini and see how we can achieve this cool effect. So here I have imported my petal geometry, which we have a UV attribute also, and I have a camera also. So here you can see right now our petals have quite high res, 47,000. Since we are going to scatter petals on around 5,000 points, this mesh will be a lot denser mesh, so we have to reduce the polygon of this mesh. So first let's take a poly reduce node here, and we have to decrease this value to 2. You can see this is deforming the UVs also, so to fix that we can turn this on preserve chords. So now it will have only around 890 points. Earlier we were having 47,000 points. Now this is a double sided mesh. We need to create a proxy geometry for the Vellum simulation. So to do that we can take a triangulate 2D node. This will make a grid based on the input. So you can see this is a single sided mesh only, and it is also following the petal shape. But the problem is, you can see on the edge we have lots of point here. So to fix this we can turn this refine on, and we can turn on this constraint edge group. Now you can see we have the edge group here. Now we can take edge group to curve node. This node is from labs, so make sure that you have installed side effects lab. So we will take this edge group to curve node, and here we can select the group as constraint edge. This will give the curve which we require. Now we can take a resample node here, and we can reduce this value to 2. Now we have this kind of curve. Now we can take a add node here, and then go on the polygon and switch this to by group, and we can make this to close. Now you can see we have a nice geometry here, but you can also see that we have our curve also present on the geometry. You can see we have 2 polygons here. So we can take a blast node and we can delete the first polygon. You can see here we were having curve. Now we will have only our geometry. Now we can take a remesh node here, and then let's keep the default value only, no need to change it. Or else you can also go on a adaptive method and set the minimum and maximum size, but make sure that if you want that extremely highly detailed simulation, then you can adjust this parameter according to your need. But for now I will go around these values. Yep, we can also decrease this to 1 1. Now we can create a group. This will be our tech group, tech mesh, and here we can make this as a render group, render geo. Let's merge both of this. Cool. Now we have to take a grid node here. Let's adjust the size. We will keep this to 2 by 2, and let's increase the rows and columns to 50. So this will be our simulation area. We are only using small amount of the 3D space because it will, if we make it in a real scale, then the mesh count will be so much and it will crash my PC. So now let's take a group node here, and we will take camera frustum QL. So this node is from QLib. I will give all the third party OTLs link in the description. This all are free of course, so you can download it. Now you can see this will create frustum for our camera. We can connect this here, and let's change the group name to delete, and on the group type we will keep it to point. We will turn off this base group and we will turn on the bounding region, and here we have to select bounding objects and make sure to make it to 0. Now here we have to increase the overscan. Let's make it to 0.1 by 0.1. Now we can take a blast node. Now we can take a scatter node here, and we will scatter around 3000 points. Let's change the global seed. Now we can take a attribute wrangle here. So if we suppose I will take a copy to point node, and I will copy this. So this will copy our geometry in the same orientation. If I take a attribute noise float, this will add p scale to our points. Then also you can see all the petals are in the same direction. So to fix this, what we can do, if you see this render, my points are over here, the center, and all the petals are facing on the center. So to make that kind of orientation, we will write few lines of code. So let's do it. So what we have done here, we have stored the current point position on a vector attribute called pos, and the target point is our center. That's why we have keep 0 on all the axes. Now we can take another vector which we'll call direction, and then we can normalize it based on the target minus position. So this will be our target minus by position. And now we have, since we have our direction attribute, if we can visualize this, so we at did is equal to did. Now if I visualize this, you can see, let's make it a vector trail. How marker. So you can see our vector trails are pointing on the centroid, but we have to make this vector as a orient attribute, then only it will get read by the copy to points. So for the orient attribute we need the up vector as well. So let's create the up vector. So we will make it 0 1 0. So the up vector will always be the y axis, positive y axis. Now we have to compute the side vector also, because in the orient it is a 4 float quaternion attribute. That's why. So let's calculate the side vector also. Side dir is equal to normalize. This will be our dir up comma dir. Okay, sorry, I have to take cross vector of this, and then we will normalize it. Then this will be have our, on this line we will have our new up vector, which will be the cross product of the direction and the side. So we will write direction and then side dir. This will be our new up vector. Now we can take a matrix 3, the name will be M, and then we will set our new matrix attribute. So side new up, comma B. And here we can now set our orient attribute. We will use the quaternion function and then M. Now if I visualize the orient and I turn on this, so this is not working because while we are assigning any variable to the vector, we have to give the curly bracket, but I have just give the normal brackets only. So let's give curly bracket here. So now you can see our blue line is facing on the center. Now if we turn on this copy to point, now you can see all our petals are facing on the centroid. Now we have to assign a p scale attribute. So take attribute wrangle again. We can type f@p scale is equal to 0.1. Cool. Now you can see we have a lots of penetrations. We will go on a method to remove all those penetrations. First we have to save this point position attribute on a vector. So take another attribute wrangle, and here we will write v@my root point is equal to @p, the position of the current points. And then we will also save attribute called original point id. This will be our pt-num. This attribute we will use for the wrapping, because the petals are very close to each other, so the wrapping will cause some problem. So it's better to save attribute on the before the simulation only, and then we will use the same attribute for the wrapping. Now if we will scatter both of this will crash our PC. So let's turn on this pack and instance, then let's connect it here. Now you can see this is our petals facing on the center. Now we can unpack this, and we have to transfer our two attributes which are my root points and auric ptid. Then we can take a split node here. As you remember, we have created two groups, render and techmesh. We will split the rendered geometry here, and we will take a null here. Wrap, this will be our wrap geo, and this will be our techmesh geo. These are all the single sided mesh. Now we can take a group create node here, and then we can turn on keep on bounding region, and we can adjust the bounding box. We have to select the root points of this, because we have to pin to constraint it. And now we will name this group as root pts, and then we will make another group. This will cover our whole geometry. We will name this as a pin group. This will be our pin to soft pin constraint group. Now we have to as you remember, we have transfer our my root point attribute here. So we can take an attribute wrangle node here. If we type v@p is equal to v@my root point, so this will all my root point. This will all move to its original scattered point position, and then we can take a blend node here. Blend node, then we can blend this between the root point and the actual position. So our main motive is to remove all the interpenetrations. We will scale down the petals to its root position, and then we will scale up in the simulation using the arrest blend node. So the easier way for this method is one node called arrest position QL. This node is also from the QLib package from where I have used this. So you can download this from the link in the description. And here we can go on the restore. We will select my root points. Then we can animate this blend attribute. Okay. So on the frame 1, we will keep this to very small amount. Make sure that you will not make it to completely 1, or else the simulation will get explode. So we have to make it around value from where the petals are not penetrating on the first frame. So the 0.93 looks decent to me. Okay, let's keep it around 0.5. Yeah, 0.5 look perfect. We can give a key to this, and on the frame 30 we can make this to completely 0. Then we can take Vellum configure cloth here, and let's visualize the thickness. So for the thickness, we will all give it to set uniform, and the thickness we don't have to give this much. We'll keep it very less, like 0.00015. And here on the mass, we will also like keep it to very low. Okay, 0.0001 looks fine. Then let's decrease the normal and tangent drag, and we don't have to change all this parameter, just change the bend stiffness to 0.1, and the damping also we will reduce it to 1. Then we can take Vellum constraint node. This node will be for the pin constraint. So here on the constraint type, select pin to target. On the group type, select points, and here we will choose root points. Then here on the pin type, we will select soft constraint. On the constraint pin orientation pin type, we will choose none, and we will turn on match animation, and here we will just keep it to 1. Then take another Vellum constraint. Here also we will select pin to target only, and here we will choose our pin group. This will pin our whole geometry, not just the one point. And here also the same setting will apply, soft none, match animation turned on. But on this one we will keep the stiffness multiplier to 0.0001, and the stiffness value will be 0.5, so that it will move like it will settle down the points which are penetrating. Like if these points are penetrating, if the value is so high, it will try to maintain this position only. But if we loosen the value, it will like just bend the petals, but not that much. And we will increase the damping ratio also. This will just remove the jitter and all kind of stuff. Now we can take a Vellum solver node here. Let's go on the first frame, connect all of this node here, and we have to decrease the friction. Let's keep it to 0.005 and dynamic scale to 0.001. And we have to increase our collision passes so that it will calculate the collision more perfectly. And here on the grain collision, turn this off. And if we will play this won't do anything. If you see, it will just fall down or whatever, it will move like that. Now we can go inside the Vellum solver, and we can take Vellum rest blend node here, and here we have to select update frequency as each frame, and on the SOP input we will give this OP input. This will select our Vellum constraint, this one. So this is also animating now, that's why we have selected that, or else you can give this also, there will be no difference. Now if we play this will look something like this. Now this won't fall, it will grow. So I can see these petals are growing. So let's simulate around 45 frames and see how this will look. So as you can see, we got this, but it have some problem like here. So as you can see, the problem was this mask. Actually, I think it was way too high for this kind of simulation, so I kept it around 1e negative 0.8. The value will be around 1 second, so the numericals will be 0.0000. You can just write this one. So this will give us the perfect result what we needed. And now we can cache this out. Let's cache it around 100 frames and we will keep the last frame. So ipfix cache. Okay, so our simulation or cache, we have all these unwanted attributes. We can take attribute delete node. We will connect this here and this will go on this, and we will turn on this one and we will select delete non selected. So now we will have the same attribute which we were getting on this node, and now we can start a fresh simulation from here. Now this we don't need animated frame. We will take a time shift node and we will freeze this on frame 100. So this will be static. Now we have to create a marks attribute which will travel from center to like the edges of our frame. So it will be like a pulse marks attribute, like it will go boom 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 like this. So to do that, we don't have any third-party plugins, even though I tried with mobs, but I'm not too much familiar with mobs nodes. So I have created my own marks with few lines of code. So let's do that first. So our loop duration will be like we can keep around 40 frames. So we will create an integer variable called loop duration. This will be the value of 40, or else we can create a channel reference also. We can name this loop duration, and then we will take a float. This will be our time on which frame. So we will write frame percentage loop. So this will be the time looping from 0 to the loop duration frame number. So this will loop from 0 to 40. Okay, now we can take vector. So our marks will travel from center, so we will make sure to use the curly bracket. We will make it to 0 0 0, and then this will be our max distance. So float max dis is equal to, we will create channel reference for this also, max. Now let's calculate the length from the center to the max distance. So we will take float distance is equal to length of our current position minus center. Now we will normalize the distance to a 0 to 1 range. So to do that, we can take another float variable. We will take t normalize, which will be the distance normalize, fit distance, our current distance, to 0, and the max this. So distance, this is our attribute. The 0 will be our center and the max distance, which we will give the value once our code is completed, and then we will remap this into 0 point in 0 to 1, and now we will like loop this. So to do that, we will take another float, loop is equal to clamp. We can take our t normalize, no, we will keep our t this value, we will divide it. This will be our loop duration minus t normalize into 5 comma 0 comma 1. So no errors are coming. Then we can take a marks and we will assign this attribute. If we turn on this, and the loop duration will be 40 frames, and the max distance, let's adjust this to 1.5. If we visualize our marks, then you can see this will go like this, boom 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 boom, like this. So now we need the red area only on this part, not on the center. Currently it is like the red area is keep staying there only until the new marks start. So to fix that, we can take a attribute remap node. We can take a marks here and we can compute range. Then here we can make this like this, and we can smooth the steps, monotone cubic. If we visualize this, it will be like this. So currently the red area is too less. We can make this like this, so it will be like this. You can increase the edge also to make a proper smooth blending. Then we can like take another Vellum configure cloth node, and the same thing we have to do. Let's change it to set uniform. The value will be 0.0001. This also calculate uniform only, and we will keep the thickness to very less amount, 0.01. And here on the pinpoints we will keep the root PTS, and we will turn on soft, and we will turn on the match animation. And on the bend stiffness we will keep this to 0.0001. We don't need to change anything here. Now take another Vellum constraint. This will be our pin to target constraint. Pin to target, this will be the point group, and we have to select our pinpoints. And here we can turn off this source geometry, because that will like make the viewport too much laggy. And here on the pin type we can select soft, and the orient type to none. We can turn on match animation, so that it will like when the wave will come, it will then retract its position. And here on the stiffness we will keep this to 0.001. You have to play with these values, especially with the pin stiffness value. Now you can take a Vellum solver node. Let's go on the first frame. Now if I play this, this will usually fall all the leaves, petals. You can see it is falling. Let's turn on this. You can see all the things are falling. It is because of the high gravity value. So let's keep it to -1 only. And we don't have to change anything on the solver parameter. Let's dive into this. And the main thing for the wavy animation like this, which we want, like this, we have to go inside the solver, and we have to write this. We can take a geometry angle here. No, pop wind here, and we can turn on use vex expression. We can keep wind is equal to normalize v @p. So let's keep this first and see how this will behave. So you can see the wind is pushing the petal backwards from its center, but this will not retrain it back, and this all look so linear. We don't have any variation in it. So to give some variation, we can increase the amplitude to 0.2. Now you can see we will have some variation in it. You can see this. Now we have to use our marks. So if you see here, we have a marks attribute, marks. So let's multiply it here, f@marks. Now if I play this, So as you can see, this is not working because on if we go here and if we visualize the marks attribute, you can see we are not getting the animated attribute which we have here. You can see we have an animated one, but after the Vellum solver we don't have the animated one because the Vellum will take only the first frame. So to fix this, we can take a geometry wrangle here and we can go on the input. We'll select the second input as a SOP and we will give this attribute remap node and paste it here. We will copy this remap node and paste it here, and then in the code we can write. So first we will calculate the closest point based on the second input, and then we can take near point 1 comma @p, and then we can assign the let's give it f@marks2 is equal to point. We will assign it from the second input. The attribute name is marks, and since we have calculated the near point, we can type near pt. Now we will have the marks2 attribute. So here on the pop wind, instead of marks we will write marks2. Now let's visualize this, how this will look. Okay, this is throwing error. Okay, I forgot to give a comma here. Now you can see this will, the wave will come and then it will restore its position. Like this. Now if we will visualize the marks2, then you can see it will be animated like this. So let's cache this out and see how we can like wrap our original geometry to it. So take a Vellum, take a cache node, file cache. Let's cache this out. So our simulation is cached. Let's visualize this and see how this will look. So it will look like this. Now let's wrap this out to our original mesh. So for the wrapping purpose, I'm gonna use wrap node. This is also a free node you will get on the Gumroad. I will give the link in the description. So on the first input, this is same like the point deform, but this works better if we have multiple geometry to deform. So first this will go on the object which we need to wrap, and the second geometry we need a rest position. So our rest will be this, because this position and this position will be same, it will match. You can see here this will be the same position, and then the third one will give our tech mesh geometry. Now you can see we have some kind of deformation here. It is because we have not wrap based on our ID which we have created here called oric prim ID, point ID. So on the override, turn on enable, and here we will select oric pt ID. Now you can see all these problems which we were facing here will be gone. You can see now this will be a clean wrapping, and this node is open GL, so this will work very fast. Now you can see this code simulation. So if you like this tutorial, make sure to hit the like and subscribe button. You can support me on Patreon as well.